It is also very important to acquire the results of our computation by means of the qubit measurements. We should not forget that measuring the qubit state will actually destroy the superposition. As we explained before, the amplitude of the states of the qubit represents the probability with which a particular state of the qubit will be measured. This again shows the non-deterministic way of quantum computing. Even though the largest amplitude implies the highest probability for being read, it will happen that several runs of the same algorithms are needed, and each time, at the end of the algorithm, the measurement can be done, and when done multiple times, the result, which has been read out most of the times, contains the result. For doing a measurement, we need to measure the qubit and convert the analog signal we receive back from the qubit using an analog to digital converter this time. And then we apply a digital signal processing algorithm to discriminate the outcome of a measurement, whether it's a 0 or a 1. The measurement outcome can be a final result or an intermediate result which can be used to control further operations. Closely related to this measurement operation is quantum error correction and detection. We need to keep in mind that qubits are fragile and error-prone, and due to their very limited coherence time, they're exposed to errors. Therefore, quantum error correction is a critical component of the microarchitecture, and a dedicated unit is in charge of triggering periodic error correction cycles and correcting errors whenever they happen, such that they offer the required fault tolerance and provide correct results. Once the measurements of the ancilla qubits are received, a decoder will interpret the readouts and determine whether or not an error has manifested itself for which some correction is necessary. Quantum error correction is a very important functionality of this microarchitecture, as certain estimates show that up to 90% of what a quantum processor is doing is actually related to that quantum error correction activity. Another important component of the microarchitecture is the qubit addressing table, which allows us to keep track of qubits and their locations. The address and location of these qubits are basically used to update the physical address of each qubit used in our algorithm whenever it is moved from one location to the other. This addressing table is crucial for accommodating the routing mechanisms which move qubits around to enable two-qubit operations, which require the qubits to be nearest neighbor to be as close as possible. Finally, when operating all these units together, we can execute quantum algorithms and enjoy the opportunities that quantum computing has to offer in terms of computing speed up.